would like to first thank the organizers for the great opportunity to be here and as a young researcher to take part to the celebration of Vera Rubin. We were discussing yesterday with other people that she was a true role model, in particular for young women in science, but I would say in general for young researchers. And it is a pleasure to hear that she has recognized not only as a great scientist, but also as a good person. And that is a very nice thing to remember about a person, I would say. I'm glad to present today the results due to the joint effort of many people, as science is a collaborative effort. And I'm going to discuss results. So I'm going to present results from Planck, Simons Observatory, and Stage 4 collaborations, but also work done in collaboration with amazing collaborators, Katie Fries, Elena Giusarma, Shirley Hu, Massimiliano Lattanzi, Olga Mena, and Sanni Vagnozzi, who is a very bright PhD student and who became a PhD doctor a few days ago. So you may wonder why I decided to use this image from the Little Prince as a background image. And the reason is that I really like this quotation from the Little Prince because it describes a very familiar situation where you give something for granted and you cannot imagine anything special from this granted thing, but all of a sudden you realize that it's hiding a secret, there is a mystery in there, and all of a sudden this very familiar situation becomes very exciting and enchanted. And I think it represents a very poetical metaphor of the statement that Jim Peebles told us yesterday, that great science is hiding more secrets than the unveiling results that it can help understand. And I believe that neutrino physics is a great example of this familiar thing that hides a lot of secrets. Oops. I was saying that neutrino physics is one of that areas where a familiar situation can hide a lot of secrets that can push us to go beyond the limit that we think we have reached. In fact, in the standard model, we consider neutrinos as massless, but oscillation experiments tell us that indeed neutrinos are massive particles. And the problem is that within the standard model, the symmetries and the content of the standard model do not allow to describe neutrinos as massive particles. So we have to go beyond the standard model in order to understand the secrets that are hiding in the neutrino sector. In particular, what is the origin of the neutrino masses, and what is the theory that describes the fact that neutrinos are massive particles. So let me indulge in some basics of neutrino physics, what we know from other sectors, from laboratory searches in particular, and then what we can learn from cosmology. I will then move to show you the results that we know from current observations and give you some prospects from future observations. So to get started with what we know about neutrino physics from something beyond cosmology, we know that neutrinos, we know that we have three active families of neutrinos from the decay of the Z bosons, and we know that these three families transition in flight. We observe flavor oscillations of neutrinos because these flavor states are a superposition of massive states that propagate differently between the source and the observer. Neutrino oscillation experiments can measure very precisely the difference in mass between pairs of these massive states because the probability of the transition depends on this difference. The only problem is that neutrino oscillation experiments are blind to the absolute scale mass of neutrinos and to the way in which the total mass is distributed among the three massive states. So if one, in particular, we can have two ways in which we can distribute this total mass. The normal hierarchy, where the mostly electronic neutrino is the lightest one, and the inverted hierarchy, which is the other option. If we consider the case of the minimal mass, where the lightest neutrinos is in fact massless, we can set a minimal value for the sum of the neutrino masses from neutrino oscillation experiments, simply summing up the mass differences. And so we know from oscillation experiments that the sum of the masses has to be larger than 0.06 EV. The upper bound here comes from another laboratory search, which is the observations of beta decay experiment, where we measure the spectrum of the beta decay, and from deviations in the endpoint of the spectrum, we can infer the value of the, roughly speaking, of the individual neutrino masses. And from current limits from beta decay searches, we can put this large upper bound on the sum of the neutrino masses of 6 EV. So this is the situation if we don't consider cosmology. And now we can ask what cosmology can tell us, what kind of information we can infer from cosmological observables. In order to understand what cosmology can tell us about neutrinos, we have to understand how neutrinos enter the cosmological scenarios. Neutrinos were coupled to the rest of the plasma back in the early universe, thanks to weak interactions. And they remain coupled as long as these weak interactions were quick enough compared to the expansion rate. When this situation was no longer sustained, neutrinos decoupled from the rest of the plasma at a temperature of around 1 MeV, and they become free streaming in the universe, moving along geodesic. This happened at a very interesting temperature because right after neutrino decoupling, electron-positron annihilation happens, and the entropy released by the electron-positron annihilation went into the rest of the plasma, mostly photons, and so neutrinos that were already decoupled could not benefit from this entropy release. And this is the reason why today the neutrino temperature is below the CMB photon temperature, which makes extremely challenging to directly observe the cosmic neutrino background. Another interesting time is the time of the non-relativistic transition of neutrinos. Since they are massive particles, at some point they become non-relativistic. And from this point on, we can define a peculiar scale for neutrinos, which is the free streaming scale. Roughly speaking, is the distance that neutrinos can travel in a Hubble time. This scale is particularly important because on scales that are smaller than the free streaming scales, neutrinos effectively behave as free streaming particles, and therefore they cannot contribute to clustering on these scales because their perturbations are effectively erased by the free streaming behavior. On the other hand, on scales that are larger than the free streaming scales, neutrinos can contribute to clustering effectively as a cold dark matter component. We will see later why this is so important. Neutrinos, due to this very peculiar thermal history, contribute differently to the energy density of the universe because they contribute as a radiation component at very early times, and their contribution is usually parametrized in terms of this N-effective parameter. I will not say much more about N-effective, rather than this is the standard predicted value in the standard cosmological scenario, and current observations from CMB and large-scale structures are perfectly in agreement with the standard prediction. The important thing for this talk is that at late times, when they become non-relativistic, the contribution of neutrinos to the energy density of the universe is that of a matter component, and therefore is proportional to the sum of the neutrino masses. Due to this very peculiar thermal history, neutrinos have a lot of effects on the evolution of cosmological perturbations, which is the main tool that we have in order to infer neutrino properties from cosmological observations, rather than directly observe the cosmic neutrino background that we've seen is a very challenging experimental task. The first class of modifications to the evolution of the universe refer to the class of background modifications. So neutrinos can alter, for example, the expansion rate of the universe and therefore can change the way in which we compute distances in cosmological scenarios. But they can also alter specific epochs in the evolution of the universe, for example, altering the epoch of matter-radiation equality. This class of modifications are very important, but can be adjusted by tuning other cosmological parameters. We know that there are some degeneracies, some correlations between cosmological parameters, in a sense that some of them can mimic the effect of other parameters, erasing the reciprocal contributions in the evolution of the universe. There is, however, another class of effects which refer to modifications in the evolution of cosmological perturbations that are much more peculiar, and therefore they are the very important tool that we have to infer neutrino properties, and in particular neutrino masses, from cosmological observations. We have already seen the effect of the free streaming scale that is reported here as a function of the neutrino mass, and additionally to the effect of the free streaming scale, we also have a suppression on the evolution of matter perturbations due to the fact that neutrinos are massive particles. Effectively, massive neutrinos on scales that are smaller than the free streaming scale contribute to the background evolution, but do not contribute to clustering. And this slows down the growth of matter perturbations proportionally to this ratio between the neutrino content with respect to the total matter content. The net effect is a relative power suppression in the total matter power spectrum at small scales with respect to large scale. And this is the main part of cosmological observations where we look in order to infer constraints on the neutrino masses. The main observables that we can use in order to track down these footprints of massive neutrinos in cosmological observables are, of course, the anisotropies in temperature and polarization of the cosmic microwave background and the distribution of matter in the universe. So any tracer of the large-scale structure in the universe, galaxy clustering, weak lensing, either in galaxy surveys or in the CMB itself, cluster counts, and any other tracer that we can think of. Once we obtain observations of these cosmological probes, we can think of computing constraints on the sum of the neutrino masses. And I'd like to summarize the current constraints that we have on the sum of the neutrino masses in this plot, where the sum of the neutrino masses is reported as a function of the mass of the lightest state. And these colored bands here are the allowed regions according to neutrino oscillation experiments. This is the normal ordering or hierarchy, and this is the inverted hierarchy. If we consider observations from the Planck collaboration in temperature and polarization, and including also the lensing of the CMB photons, we can see that at 2 sigma we can already exclude the region above 0.24 eV. So most of the so-called degenerate region where the two hierarchies overlap perfectly with each other. If we include additional information coming from the large-scale structure of the universe, for example, in terms of the baryon acoustic oscillation observations, we can further improve the the previous limits, going down to excluding all the region above 0.12 eV. And you see that we are very close to cornering the allowed region in the so-called inverted hierarchy. So we are very close to tell us something about the neutrino hierarchy by means of cosmological observations. At this point, I have to say that these constraints are obtained in a very peculiar cosmological scenario. Not particularly peculiar, but these constraints are obtained in the so-called one-parameter extension of the lambda CDM model. The reason why I'm stressing the fact that these constraints come from the assumption of this underlying cosmological model is that we know that there is a certain dependency in the constraints on neutrino masses and in some other cosmological parameters on the underlying cosmological models. In other words, for the parameter degeneracy that we were discussing before, it is possible that by assuming different cosmological scenarios, the constraints on the neutrino masses may differ a little bit depending on the cosmological scenario. For example, here I'm showing you what happens if you consider extended scenarios in which you have a dynamical dark energy component, for example, where you have a broadening of the constraints on the neutrino masses. This is not always the case, because depending on what scenario you consider, you might also have tighter constraints on the sum of the neutrino masses. The important point here is that given the current sensitivity of cosmological surveys, there is still a certain level of model dependency of the constraints on the neutrino masses from cosmological observations. And this is probably the main challenge that we have to face with the next generation of cosmological surveys, the main issue that we have to fix in order to provide robust constraints on the sum of the neutrino masses with future observations. This is the conclusion of the current constraints, and now I'd like to introduce you to the prospect that we are facing with the next generation of cosmological surveys. We are in a very exciting era of cosmology because a huge number of exquisite sensitivity cosmological surveys is just around the corner. Given their extraordinary sensitivity, we are tempted to ask whether we are very close to detect for the first time ever the absolute scale of the neutrino masses with cosmological observations. I would say yes, we are very close to do that, but we also know that with great power comes great responsibility. And the reason is exactly what I was telling you before, the fact that we are not in a race to obtain the tightest constraints on the neutrino masses, for example, with respect to laboratory searches, but the real goal that we have to face is how to obtain robust constraints on the sum of the neutrino masses from cosmology in a way that this information can be efficiently exploited not only by the cosmological community, but by the scientific community in general, in order that we can inform, for example, model building or other experimental searches in the neutrino sector. And this robustness has to come with respect to many things, with respect to systematic contamination in our data, but also with respect to theoretical systematic contamination, the model dependency that I was discussing a moment ago. Luckily enough, we know how to reach the robustness of our constraints. We know what is the path that we have to follow in order to arrive to such robust constraints. And this path is enabled by the properties of the next generation of cosmological surveys, CMB surveys and large-scale structure surveys. First of all, we can rely on extraordinary complementarity between the different surveys. We are entering an era where the sensitivity of the different surveys is comparable with each other, which means that we can have efficient cross-check between the results that are obtained by the individual surveys. So this can increase our confidence in the constraints obtained by the individual surveys. We also have redundancy within each individual cosmological surveys. Think, for example, to the observation of temperature and polarization in CMB experiments, or galaxy clustering and weak lengthening observations within large-scale structure surveys. Each of these paths has its own systematic contaminations and its own analysis tool independent from each other, and therefore we can additionally cross-check internally the results that we obtain on the sum of the neutrino masses. And finally, we are really devoting a lot of efforts in trying to anticipate any possible systematic contamination that we can think of and find ways to either remove or alleviate these systematic contaminations in our real data. As an example, I'd like to show you the projected constraints that we can obtain with the upcoming CMB observatory, Simon's observatory, on the sum of the neutrino masses. These are constraints obtained from different analyses within the collaboration and in conjunction with the constraints coming from overlapping cosmological surveys. And you can see that comparing these numbers, where the numbers without brackets correspond to inclusion of possible systematic contaminations, whereas the numbers within brackets are in the most optimistic scenario of of negligible systematic contaminations, you can see that the constraints are similar to each other, which means that by using this individual and independent analysis pipeline, we can cross-check the results that we will obtain on the sum of the neutrino masses. These constraints can be further improved if we combine observations of Simon's observatory and other surveys with a cosmic variance limited measurement of the reionization optical depth, which is one of the most correlated parameters with the sum of the neutrino masses. Once this level of sensitivity is obtained and we are confident that these constraints are robust, we can really think of using this information as a tool for the scientific community in general. These plots are showing you the complementarity of the constraints coming from cosmology and coming from other laboratory probes of the absolute scale mass of neutrinos. For example, beta decay searches that are sensitive to this particular combination of neutrino masses and mixing parameters, or neutrinoless double beta decay searches which are sensitive to a slightly different combination of the same parameters. And you can see that the constraints from cosmology and from projected experiments, beta decay and neutrinoless double beta decay, are comparable with each other. So we can think, for example, to use constraints coming from cosmology to inform the preparation of laboratory searches, for example. Or we can think of a very interesting scenario where the constraints coming from the different probes are not in agreement with each other, and provided that we are confident that these differences are not coming from systematic contaminations, they can really point to something beyond the standard model, something that is yet to be understood in the neutrino sector. I'd like to, before concluding, I'd like to briefly mention the possibility to constrain the neutrino hierarchy or ordering with cosmological observables. The reason is that it is a truly physical effect that we expect on cosmological observables. We have seen that many of the imprint of massive neutrinos on cosmological probes depend on the neutrino masses, and so in principle the effect of the different masses in the three neutrino states is imprinted in cosmological observables. As you can see here, where the ratio of the neutrino energy density and the matter power spectrum in the case of different orderings, for example, normal hierarchy, inverted hierarchy, one massive neutrino and two massive neutrinos, are plotted with respect to the case in which the total mass is instead equally distributed between the three massive states. So the effect is there. We might think of extracting this information in order to constrain the hierarchy. And we have done this test by translating the bounds on the neutrino masses into a weighted sum of the bounds that can come by assuming normal hierarchy and inverted hierarchy, and using these different weights to tell us whether cosmology prefers one hierarchy with respect to the other. We are not alone in this exercise. There is a huge list of people that are looking into this effect, and the conclusion is that, unfortunately, given the current and probably the future sensitivity of cosmological surveys, that physical effect that is there in cosmological observables is so tiny that it might be extremely difficult to disentangle the hierarchies with cosmological probes. The only tool that we might have in order to distinguish between the two hierarchies is if we can constrain the sum of the neutrino masses to be below the minimal value allowed by neutrino oscillation experiments in the inverted hierarchy scenario. So if we are going to measure the sum of the masses to be below 0.1 eV with high statistical significance, we can conclude that the preferred hierarchy is the normal hierarchy, which is the only one that can predict such a low values of the sum of the neutrino masses. To conclude, I hope that I've given you the punchline that cosmology is really able to provide interesting constraints on neutrino properties and neutrino masses in particular, and that we are really working hard in order not only to obtain tight constraints on the neutrino masses, but in particular in order to obtain very robust constraints that can be used by the full scientific community in general. So thank you for your attention.
Thank you very much, Martina. Questions? Okay, you're not a young person, but please.
I used to be a young person. It was only 75 years ago. Yesterday, we heard about a number of experiments where the sensitivity had improved by thousands or 100,000 in a year or two. The thing that strikes me is, although your results are very impressive, they're not much smaller than the limits that Zeldovich got in the 60s and Kausick and McClellan in the 70s, just by saying the universe is not closed by neutrinos. We've only improved about 1.5 orders of magnitude in 40-some years, 50-some years.
Yeah, I think that the name of the game here is really to obtain robust constraints rather than just bringing down the upper limit on the sum of the neutrino masses, because that is something that, for example, other communities are requiring to cosmologists to give robust constraints with respect to the underlying cosmological model, for example, in a way that can be really exploited by other communities.
Yes. Let's try to get you a mic. Yesterday there were people bringing mics, but...
Thanks. So I know Simon's Observatory is supposed to improve the sensitivity of like the current stage 3 telescopes by, what, an order of magnitude, with like an order of magnitude more detectors. And that one of the biggest problems that you mentioned was such a heavy dependence on models. So are the limits on the constraints that we're going to find for the sum of neutrino masses limited more by the instrumentation or by the models?
So I will say that those limits, the limits that I showed you, can be further brought down with the stage 4-like surveys. So part of the constraints can be improved with high sensitivity, further high sensitivity experiments. But the real limitation on these constraints come from model dependency, in a sense that unless you have different probes that you can combine together, as we will think will happen in the next future, you are limited by the extension of the underlying cosmological model that you can consider. For example, if you consider more exotic or more extended scenarios, not only the sigma in these constraints can be different, but they can also be shifted with respect to the best fit value. So the key point is to have surveys as the surveys that we'll have in the future that will be sensitive to different effects of the neutrino masses in this particular case in order to limit the effect of model dependency. And we believe that we are very close to obtain this level of robustness.
However, I do want to advertise something that Martina did, which is that, yes, most of this work assumes lambda CDM. However, if you have a dark energy, even dynamical, in which W is always greater than or equal to -1, the bounds are tighter. So that particular model dependence is not a problem. So dark energy is not going to change the results unless W is less than -1.
Okay, while John is setting up this question from Net.
So that was very nice and important how you emphasized the checking for robustness among the different methods, not just the uncertainty reduction. But if we look today, for example, at Planck that you used, and the differences or the tension that they get in Hubble constant, omega matter, sigma 8, all these cosmological parameters between the Planck results and some of the other large-scale structure surveys, how would that affect some of the measurements that you did for neutrinos?
At the current stage, the effects that are coming from the modifications to the perturbations are only slightly more important than the background effect. So this is the reason why with current data, the problem of model dependency is larger than it would be in the future, because you can change some background quantities, for example, as we were mentioning, the dark energy equation of state, depending on what model of dark energy you consider, and you can have different upper bounds on the sum of the neutrino masses. But in the next years, when the effects on the on the evolution of perturbations will be much more important in terms of sensitivity to the sum of the neutrino masses with respect to the background effect, this model dependency will be cured, and I believe that it would be much more mild with respect to the tensions that you were mentioning between high redshift probes of some quantities as the Hubble rate, for example, with respect to low redshift probes, because the effect of the neutrino masses are really integrated over different cosmological probes. So by combining them, we will be able to really leverage down the sensitivity to the sum of the neutrino masses.
All right, let's end it there. Let's thank Martina. Sorry, one more? Well, I think we're quite running behind, so let's leave that question to the break. Let's thank Martina again for a very pedagogical talk.